Today, we're pulling back the curtain on the invisible world of digital simulation. It's the science that lets us build, test, and even break the most complicated products you can imagine, all before a single physical piece even exists.
I mean, just think about it. How can an engineer look decades into the future to see exactly where rust will weaken a huge offshore rig? How do they know which part is going to fail first?
Or what about something you see every single day, like a tire? How do you even begin to understand the incredible, complex forces at play on every little piece of rubber and steel as it's screaming around a corner? And it's not just about giant structures. This same technology lets us zoom way in to predict tiny, microscopic stresses and warping in a 3D printed part as it's being born, layer by delicate layer. It all comes down to this one huge question. How do we know? Well, the answer is kind of like a digital crystal ball, a process that lets us see what's completely invisible. This is the world of the engineer, and this is their journey.
Okay, let's get into it. Every single simulation, I don't care how complicated it always starts with the same basic step. You got to build a digital version of the thing, a kind of digital skeleton.
In the engineering world, we call this skeleton a mesh. You're basically taking a complex 3D model and breaking it down into thousands or sometimes millions of simple connected shapes. Think of it like a high-tech digital sculpture. And let me tell you, the quality of this mesh is absolutely critical. It can literally make or break the whole thing.
But right out of the gate, it's not that simple. Let's say you're simulating how air flows over a car. That's a field called computational fluid dynamics, or CFD. Well, engineers have to pick the right tool for the job. Two of the big ones are ANSYS meshing and fluent meshing, and they have two totally different ways of thinking.
And this difference in philosophy is really key. One tool, ANSYS meshing, is all about flexibility. It's like a workshop where you can mix and match different methods, tweak things whenever you want. The other, fluent meshing, is more like a guided tour, walking you through step by step. There's no one right answer, you see. It's all about picking the right tool for the problem you're trying to solve.
So once you've built that mesh, how do you actually, interact with it? This gets us to a huge, long-running debate in the community, and it's almost a philosophical choice. Are you a code person or a clicks person?
This quote from an engineer on Reddit just nails the heart of the debate. On one side, you've got APDL. It's a powerful scripting language that gives you total, fine-grained control over every little thing. On the other side is Workbench, a modern, graphical interface that's way faster and more intuitive for a lot of jobs. So here's the deal. With scripting, you get this unbelievable control and the power to automate really complex, repetitive stuff. But, man, the learning curve is steep. The graphical interface Workbench is way faster for setting up simpler models, and it's easier to learn. But some old-school engineers feel like it can be a black box, hiding what's really going on under the hood.
But here's the thing you have to remember. Simulation is not a magic button. It's a craft. It takes expertise, intuition, and a whole lot of troubleshooting. So, what happens when you build the model, you set everything up, and the simulation just fails?
Picture this. An engineer spends hours, maybe days, setting up this model of a wheel. They hit solve, feeling good, and then this cryptic message pops up. An internal solution magnitude limit was exceeded. What this really means is that the whole simulation just broke. A part of the model is mathematically just flying off into space.
Now, the first instinct might be to just start randomly changing settings, right? But a real pro knows you investigate first. They use a special diagnostic tool to check how all the parts are sitting at the very beginning. And that's where they find it. A tiny, microscopic gap, a little flaw from the original design that's keeping the wheel from touching its shaft. And this is the beautiful part. The solution isn't some super complex workaround. It's a single setting, adjust to touch. You're just telling the software, hey, see that tiny gap? Close it. And with that one click, the model solves perfectly. It just goes to show you how deep expertise can lead to a really simple, powerful fix.
So after all that meticulous work, the meshing, the setup, the debugging, what's the big payoff? Why does any of this stuff matter? Well, let's take a look at how simulation is actually changing the world around us.
Think about testing the little solder joints on a circuit board. What used to be a manual process that could take an expert 3 or 4 weeks can now be almost completely automated. This lets engineers test dozens of designs in the time it used to take to test just one. Ever hear that faint, high-pitched whining sound from one of your electronics? That's often something called the singing capacitor effect.
Well, here, simulation is being used to predict the exact sound level caused by that vibration, helping engineers design quieter gadgets right from the start.
And hey, we're back to that offshore rig. This isn't just a pretty picture, it's a safety roadmap. The simulation can predict the service life of every single component, from 70 years for one part to over 300 for another. That allows for targeted, smarter maintenance and keeps the whole structure safe.
You know, modern products are just too complex for any one person or team. That's why simulation is moving to the cloud. An electrical engineer in one country can upload their model. A thermal engineer in another country uploads theirs, and the two models are connected and simulated together, all while protecting everyone's confidential designs. It's true collaboration.
So we've seen how engineers build these digital skeletons, the tools they use, how they solve problems, and the amazing results in the real world. So, where does this journey go next?
The future is something called the digital twin. And this is a total game changer. It's not just a static simulation anymore. A digital twin is a virtual model that's being constantly updated with real-time data from sensors on the actual physical object. The simulation doesn't just predict the future, it mirrors the present, learning and changing right alongside its real-world counterpart.
And that brings us to a final thought. For centuries, the only way to really understand how something worked was to take it apart, to push it until it broke. Simulation changed that. So as this technology gets even more powerful, connecting the digital and physical worlds, it really makes you wonder,